Dear friends, today we will discuss dielectric and dielectric polarization. Before discussing about dielectric, let's try to understand what do you mean by polar molecule and non-polar molecule. So molecules are classified here into two types. Molecules are classified into two types. One is polar molecule, one is non-polar molecule. So what do you mean by polar molecule? I have told you while discussing electric dipole, practical example of electric dipole in day-to-day life. The one wrong conception was in your mind. The plus q minus q charge separated by finite distance are called as dipole. Why they are not attracting each other? This wrong conception was in your mind. But at that time, while discussing about electric dipole, I told you to remove that type of wrong conception. Actually, what is dipole? In practical life, what is dipole? You just recall. At that time, I had told you dipole means it's a molecule where positive and negative centers are separated by a finite distance. So that one is called as polar molecule. The molecule having permanent dipole moment is called as polar molecule. Again I am repeating also that one. I have told you about H plus Cl minus. HCl is a molecule, but H plus and Cl minus, there is some separation between their center. It's called as a dipole. It has permanent dipole moment, and this molecule is called polar molecule. And also another example I have told you, H2O. This is O, this is H, this is H. There is some bond angle. We are not bothered about that. But I have told you this is minus 2, this is plus 1, this is plus 1. And plus 1, its center is here. So plus 2. Minus 2 plus 2 separated by some distance. I have told you also water molecule is a dipole. So water molecule is a polar molecule. It has a permanent dipole moment. So now if you understand, what do you mean by polar molecule? The molecule having permanent dipole moment is called as polar molecule. Then we will come to what do you mean by non-polar molecule? Non-polar molecule. Now let's come non-polar molecule. I told you also there, just I am reminding you, CO2. CO2. See, carbon make 4 bonds. It is tetravalence nature. Then here minus 2, plus 4. Carbon dioxide. Okay. So carbon dioxide, where is the positive center of carbon? Here. And where is the negative center? Also minus 4 here. So plus 4 and minus 4 are separated by some distance. Are they separated? Not. Positive center coincides with negative center. But here positive center, negative center are separated by finite distance. And has some permanent dipole moment. Here finite distance has some permanent dipole moment. But what about here? Here plus 4 and minus 4, they lie at same points. Means there is no separation between positive and negative center. Is it electric dipole? No. It has some dipole moment? No. It has no dipole moment. It is no permanent dipole moment. So it's a which type of molecule? It's a non-polar molecule. The molecule having no permanent dipole moment is called non-polar molecule. Its a positive center and negative center coincides with each other. So this is called non-polar molecule. I think you better understand now what do you mean by polar molecule and what do you mean by non-polar molecule. But can a non-polar molecule, in a non-polar molecule dipole moment be developed? Can you develop dipole moment in a non-polar molecule? Yes. we can develop dipole moment in a non-polar molecule. How will develop the dipole moment? Now you see, this is carbon dioxide. Okay, so now see, you apply one positive field, positive plate and a negative plate. You keep the molecule in an external electric field. Suppose external electric field is E, electric field intensity in this direction. Now you just keep the molecule in external electric field. Now what will happen? If I keep from the starting, the molecule has no permanent dipole moment. But if I keep the molecule in external electric field, you see, so this negative plate, this negative charge of the field will attract the positive center. This positive plate of the field will attract the negative center. Now what will happen? From the starting, what happened here in carbon dioxide? Plus minus both lie on same point. Plus minus both lie at same point. But when this field is applied, so what happens here now? Towards positive minus is attracted, towards negative plus is attracted. Okay. Is there some separation now? Are they coincide? Are they coincide? No, they are not coinciding. Is there some separation? Yes. Now there is some separation. Little separation will make it a dipole. Will make it a dipole. Now it has dipole moment or not? Yes. Is it? It's permanent dipole moment? No. Only polar molecule has a permanent dipole moment. It is this the permanent dipole moment. It is the dipole moment. What word we will use? Induced. Induced dipole moment due to external electric field. Okay. So in a non-polar molecule, also we can induce dipole moment by the application of external electric field. It can behave as a dipole. But now one question is coming to your mind. If we increase this field strength, suppose this field strength will be more, this positive will attract this negative more, this negative will attract this positive more, separation will be more. If separation will be more, what happens to the dipole moment? Dipole moment is charge into distance of separation. If distance of separation is more, you see, charge into distance of separation. Charge is constant, plus minus constant. But what about this distance of separation? If electric field strength increases, distance of separation increases. If increases, what about dipole moment? Increases. Dipole moment increases. Means dipole moment, how much will induce? I am writing small p here, but it is molecule dipole moment. Okay. This dipole moment, how much will induce, depends on external electric field. More is the external electric field, more is the induced dipole moment. What is the relation? Directly proportional or inversely? Obviously, directly proportional. So let's write the relation. Directly proportional epsilon naught, directly proportional E. Electric field applied, but we have to write here one epsilon naught. Why we are writing this? To make the dimensionally consistent. To make one equation will come, to make that equation dimensionally consistent, so it will obey the dimension law. Okay, for that, to make both sides same dimension, epsilon naught is added here. Now what will do? I have to multiply one constant. This dipole moment proportional to epsilon naught E. But I have to multiply one constant. What is the constant here? Alpha is the constant. This is directly proportional sign. This is alpha. Just distinguish them, both are looking same. So this is alpha. Alpha is the constant here. And what this constant is called? Molecular polarizability. It's called molecular polarizability. This now induced dipole moment is developed. It becomes a dipole. So this constant is called molecular polarizability. And one magic you will see when you will find the unit and dimensional formula of alpha. You will find its unit and its dimensional formula of alpha. You will see one magic. Okay? So that's up to you. You will find the dimensional formula. I have given you the formula. This is dipole moment of molecule. You know this is epsilon naught. You know this dimension from Coulomb's law. Okay? And this is electric field intensity. You also know the dimension. You put the dimension and find the dimensional formula of alpha. Okay? Then you will see the magic. So now this is about how the molecule classified into two types, polar and non-polar. Again I am telling you, polar molecule means molecule having permanent dipole moment. Non-polar molecule means molecule having no permanent dipole moment, but dipole moment can be induced when it is kept in external electric field. Now the question comes, if we will take specimen of this polar molecule, specimen of this non-polar molecule, then what will happen? Specimen means I will take material. You see, now I will take material. I will take a lot of polar molecules. Okay, I will take a lot of polar molecules. Now here many molecules are here. All molecules have one dipole moment. Lot of polar molecules are here. Okay, so I will take here a lot of non-polar molecules. This is non-polar specimen and this is polar specimen. Then what will happen? In this is polar specimen, if one molecule, each molecule has some dipole moment, suppose there are 100 molecules, then what will be the total dipole moment? 100 into dipole moment of each molecule. I am again repeating, you listen. Here each molecule has dipole moment. Each molecule has dipole moment. Suppose there are 100 molecules, then what will be the total dipole moment? 100 into dipole moment of each molecule. It should be the calculation. No, but practically this doesn't happen. Why this doesn't happen? You know dipole moment is a vector quantity and the dipoles, each molecule behave like a dipole. This is a molecule actually. Here is a negative charge, here is a positive charge, here negative charge, here positive charge. It's a molecule. Arrow means it's a molecule, it's a dipole moment direction, it's represented here. So one molecule if is directed like this, then one molecule is directed like this. One molecule is directed like this, one is like this, one is like this, one like this, like this. Now you see what is the situation. Now you see what you mark. They are randomly oriented due to thermal energy. You ask the question why they are randomly oriented? Because they have the thermal energy, temperature. Room temperature is 300 Kelvin. You know molecules always measure temperature in Kelvin. You measure in Celsius, but molecules measure in Kelvin. Okay, they are very sensitive. Then they are always you take the unit of temperature Kelvin while discussing about molecule. Okay, so now 300 Kelvin temperature, even if at room temperature, they orient randomly. What is the total dipole moment of this polar specimen? 0. If you do the vector addition, it will be 0. And what about this non-polar? Its molecule itself has no dipole moment. What about the dipole moment of the specimen? What about the dipole moment of the substance? Specimen means I am telling the substance having many molecules. It has also no dipole moment. So this I discussed about polar and non-polar. So now we will go to one important part here. What our topic today, dielectric. Dielectric. What do you mean by dielectric? Dielectric, this word comes from dia plus electric. Dia plus electric. Dia means it's a Greek word. The meaning is through. Dia means through and electric is electric. What do you mean by dielectric? What is this? Since 2 chapters we are discussing only always about dielectric medium, but I have told you we'll discuss the dielectric at the end of the 2nd chapter. What do you mean by this dielectric? I have only given the information. It is an insulator. not a conductor, but little different from insulator. Not all insulators are dielectric. So today we'll discuss about this. So what do we mean by dielectric? So dielectric is a substance, or it is a poor conductor of electricity. It is an insulator through which electricity cannot pass, electric current cannot pass. It is an insulator. Obviously electric current cannot pass. That you know. But what extra? Extra is, but electric field can pass through it. You see, its name is written like this because electric field can pass through it. So dia means through electric field. Electric field can pass through it. It's called a dielectric. Electric field can pass, but electric current cannot pass. How it is different from conductor? How it is different from conductor? In conductor, what happens? Electric current can pass. Current can pass, but electric field cannot pass. Now you see what is the difference between conductor and dielectric. In dielectric, electric current cannot pass, but electric field can pass through. But in conductor, electric current can pass, but electric field cannot pass. You know, electric field touch the surface of conductor at perpendicular but cannot enter through it. This is the basic difference. I hope you have now a little idea about what is dielectric. Also I am telling you, this dielectric, when it's kept in external electric field, it gets polarized. Now that one we'll discuss today about polarization of a dielectric. So this much idea now you have. Dielectric as an insulator through which electric current cannot pass but electric field can pass. And also moreover, its molecules can be polarized, can convert into dipole. Its molecules can be polarized, means converts into dipole. Then that is the dielectric. Now see, dielectric is of how many types? What are the two different types of dielectric? One is polar dielectric, polar. Another one is non-polar dielectric. What do you mean by polar dielectric? Polar dielectric means the dielectric which contain the molecules having permanent dipole moment. Means dielectric containing polar molecule. What is non-polar dielectric? Dielectric containing non-polar molecule. That is non-polar dielectric. And already I have told you what is polar and what is non-polar. Okay? But what about the total dipole moment of the dielectric? Zero. Because just before I told you, if you take polar substance, dipole moment is zero. If you take non-polar substance, also dipole moment is zero. What is the dipole moment of the dielectric? It is zero. But when we keep in external electric field, now see what happens. If we keep in external electric field, now see what happens in dipole. Okay, so this is one dielectric. So now I am discussing about polar dielectric. This I am discussing first. Suppose this dielectric, here the dipoles, they align like this, randomly oriented. This is the dielectric, having no dipole moment, but molecules have dipole moment. But now no dipole, total dipole moment is zero. Even if you take non-polar dielectric, also dipole moment is zero. But if you apply external electric field, you see, I am applying one external electric field. This is one positive plate. This is the negative plate. Okay, positive plate, negative plate. I am taking some charges. Here is the dielectric. I am leaving some gap here. See, this is the dielectric. What happened? You apply one external electric field. Let's write the electric field is E naught because it's in vacuum. So let's write as E naught. Now, so this here the molecules is randomly oriented, or no dipole moment of molecule. It may be polar dielectric, may be non-polar dielectric. But what will happen if you apply external electric field? Now the molecule, suppose one molecule is like this. You see, this is the dipole moment of the molecule. You apply one external field like this. You see, this is the external electric field. You just recall. What is the angle between them? Theta. Does the dipole remain like this? Does the dipole remain like this? No, I have told you. When some angle is there, immediately what happens to dipole? The dipole will rotate. The dipole will experience torque. P sin theta. And come to which position? Stable equilibrium position. Theta is equal to 0 degree. We have discussed in torque on dipole. Theta equal to 0 degree means what about this dipole? This dipole will turn and will align along the direction of the field. Not the situation of one dipole. You take this dipole, this one dipole that is aligns like this. This dipole aligns like this. Okay, all dipoles they align along the direction of electric field. Here one dipole, here one dipole. You see the dipoles now aligns along the direction of the electric field. Now you understand. Now the dipole will have permanent dipole moment or not? Yes. Now the dipole will have permanent dipole moment. Dipole moment of each molecule into number of molecules, then become total dipole moment of the system. Okay. Now see what happens inside the dielectric. Now see what happens to the inside the dielectric. Okay, this dielectric has now permanent dipole moment. The whole dielectric has permanent dipole moment. Dipole moment of each molecule into number of dipoles present. This is the total dipole moment of the dielectric. Okay, now come what happens inside it. Okay, so this is the dipole, means this side is negative charge and this side positive charge. So this side negative charge, this is positive charge. This is negative charge, this is positive charge. So like this, negative, positive, negative, positive, negative, positive. Okay, here also negative, positive, negative, positive, negative, positive. So this is one molecule. They align along the direction of the field. Okay, I can also make them as one molecule. You see, this is one molecule. This is one molecule. This is one molecule. This is one molecule. This is one, and this is one. This is one molecule. They align like this. But what happened? The more is the electric field strength, or in that electric field strength also you see this positive, you mark this positive. This positive is attracted where? To along I cap, to that side. This negative is attracted where? This negative is minus I cap towards positive plate. So this positive and negative, now they cancel each other. So now you erase this one. Positive, negative, now they cancel each other here. Here the same situation also, positive, negative. They cancel each other. So what will happen? Now what remain, you see? What remain? This side and this side. Which charges remain here? Minus. And here which charges remain? Plus. What happens to the dielectric? This surface become negative charge, this surface become positive charge. Means charges are induced in the dielectric. Induced word is again coming. In the first chapter we have discussed the induced word. Is that the main cause of induction? Because I have told you, when you take some positive charge, its nearer end becomes negative, further end becomes positive. Is that the cause of induction? Yes, this is the cause of induction in insulator. But what is the cause of induction in conductor? Their free electrons move to one side, the other side become positive in conductor. In conductor, in induction, what happens? Free electrons shift. But here in insulator, how the induction happens? Also induction happens in insulator. You have taken the plastic scale and also touch with a small piece of paper. Small piece of paper, are they conductor? No, they are insulator. But they get attracted by the plastic scale by method of induction. You know, small piece of paper are insulators. Okay, so they get attracted by the charged plastic scale. Charge attract on charge body. Small piece of paper, how? By method of induction. So in insulator also induction happens, in dielectric induction happens, but how? This is the way. Here is the negative charges comes to this end. I explained you the whole process what happens. This is the way. At that time just you had remembered like this, but today now you understand the real cause of induction. Many more things also you will understand. The real cause of the many more things you will understand. You just wait and watch. So here are the negative charges. Here the positive charge induced. So this is the external electric field surface charge density. I like this is plus sigma. This is minus sigma. But here also charges developed. Okay, due to this external electric field. And here its charge becomes, I am writing this minus sigma P. P stands for, I am writing P only symbol. This is the induced charge surface charge density. And this is plus sigma P. Suppose this dielectric has some separation D. Surface separation is D. And dielectric has also some surface area of this surface. It is a three-dimensional figure. It has surface area of this side surface. Suppose that surface area is A. Then the dielectric has the volume A into D. A into D. This may be cube, may be cuboid. So A into D. Okay, volume. And here is the surface. This is induced surface charge density. So now you see, so inside the dielectric one, electric field is induced. You see, this is the positive, this is the negative. So here is one electric field or not, but where is the direction of electric field? It is here, opposite to the applied electric field. Electric field is in that direction. But now induced electric field in opposite direction to the applied electric field. Now you understand one thing. When you keep dielectric between two charges, force decreases. Why force decreases? Now you will understand that one. You are just remembered like that, force decreases. But now you understand why force decreases. Now see what is the total electric field inside the dielectric. Total electric field inside the dielectric is E naught minus EP. Why minus? Because they are vectors and in opposite direction. So what is E naught? Sigma by epsilon naught. This is I cap. This is I cap. And what is EP? Sigma P by epsilon naught. This is sigma P by epsilon naught. This is plus minus I cap. So it will become sigma by epsilon naught. Sigma P by epsilon naught. This is I cap. Okay, so this is the net electric field inside the dielectric. Net electric field. Sigma P is always less than sigma. Again you remember, I have told you, induced charge always less than inducing charge. So sigma P is always less than sigma. Induced charge always less than inducing. So this is inducing, this is induced. Less. So sigma P always less than sigma. Okay. What about the electric field inside dielectric? So E always less than E naught. Net electric field inside the dielectric, net electric field, I am not telling EP. I am telling after subtraction. This electric field, net electric field. Net electric field is always less than E naught. Now you understand why inside dielectric electric field decreases? Also you are able to understand why the force electric field decreases, so force decreases. If electric field decreases, the force decreases. Because whenever you keep dielectric, suddenly it induces another electric field opposite to our external electric field and cancel our electric field. So electric field inside the dielectric decreases. This is the reason why it decreases. But if it is a conductor, what happens? Another important thing also will be clear now. I have told you I will explain that one at the end of the chapter. I am going to that point now. If it is a conductor, what happens? Sigma is equal to sigma P. If it is a conductor, induced charge is equal to induced charge. If it is a conductor. If inducing charge and induced charge both are same, E is equal to sigma is equal to sigma P. What about the electric field inside the conductor? If it is conductor, it is the electric field inside what? Dielectric. But if it is conductor, sigma and sigma P both are same. See the electric field? 0. Now you understand why electric field inside conductor is 0. What happened? When you give external electric field to a conductor, when you apply external field to a conductor, conductor rigorously interact with the external electric field and induce another electric field exactly equal in magnitude and opposite in direction to your external electric field, and net electric field inside the conductor becomes 0. They cancel totally the external electric field, making the net electric field inside 0, because conductor interacts rigorously, but dielectric cannot. Dielectric cannot induce that much electric field. It's dielectric. That's the conductor. So in conductor, net electric field becomes 0. Now you can able to understand why net electric field inside conductor is 0. Because external electric field is induced electric field are equal in magnitude, opposite in direction. So cancel each other. So what is dielectric constant now? All dielectrics do not show same interaction. The charge induced in all dielectric should not be same. You know, dielectrics are different examples of dielectric in our day-to-day life. Okay, I have not told you. I am telling you the examples of dielectric in day-to-day life. You can tell your ceramic dielectric, paper dielectric, mica dielectric. They are all one dielectric. Your pure water, H2O, is also one dielectric. But excellent dielectric is your dry air. Dry air is an excellent dielectric. But another dielectric also I am telling you. But your water is fair dielectric, but again more excellent dielectric is vacuum. Vacuum is one more excellent dielectric. Okay, so dielectric now, what happens here? All dielectrics do not interact same. If all the dielectrics are not interacting same, then we define one quantity to distinguish them called dielectric constant. Again dielectric constant is coming here. Here the actual definition will discuss. So why dielectric constant we should discuss. Okay, so dielectric constant K, how we define? Because all dielectrics do not show same interaction. What happens here? Dielectric constant. So this is E naught by E dielectric. This is the dielectric constant. E naught means external field applied, but E dielectric means net dielectric inside the substance, not induced. I am telling net means E naught minus EP. Means E naught minus EP, the net electric field inside the substance. This is the E dielectric. In this way, dielectric constant is defined. How much electric field is in air? When you keep the dielectric, how much electric field comes now with the net. Okay, that is the E dielectric. And you know always E naught is more, because I told you when you keep dielectric, electric field decreases. If always E naught is more, always dielectric constant is greater than 1. Always dielectric constant is greater than 1. But what happens to conductor? If you take conductor, let's discuss. What happens to dielectric constant of conductor? I told you its dielectric constant is infinite. And also I have told you, I will tell you at the end of the second chapter why dielectric constant is infinite. Okay? Why dielectric constant is infinite? When you take conductor E naught by E conductor. And E naught, what about E conductor? Now 0. So what about dielectric constant? Infinite it will be. So dielectric constant value varies from 1 to infinite. 1 for what? 1 for vacuum. 1 for air, not for air. For air, dielectric constant is 1.0008, something like this. Some decimals, then one number is there. Okay, dielectric constant of air. So air and vacuum are taken almost same, but not exactly, completely same. Vacuum is the perfect dielectric. Is a vacuum. Perfect, because nothing is there to be polarized. That is the vacuum. Excellent dielectric, that is vacuum. So this is about the electric field inside dielectric. But now we'll discuss what do you mean by polarization. Polarization polarization is a quantity. It is defined as dipole moment induced inside the dielectric per unit volume. Dipole moment induced inside the dielectric per unit volume. Just before I told you this is the dielectric. Here I told you how minus charge is induced. Here plus charge is induced. Here is the external electric field applied. This is sigma plus sigma, but this is minus sigma p. This is plus sigma p, and here is minus plate. Okay, this is the minus plate minus sigma. Let's say distance is d, and the area of this surface is a three-dimensional figure. Area is L. So here dipoles, now dipole moment induced when initially the dipoles are randomly orient, but when you give external electric field, the dipoles now start aligning themselves. Now dipoles are aligned, but at a time all dipoles are aligned. At a time, no. First, some dipoles are aligned. When some dipoles, suppose some dipoles are aligned inside it, then the dipole moment is, suppose 5 dipoles are aligned. Dipole moment is dipole. Now total dipole moment of the dielectric is how much? Each dipole moment of each molecule into number of molecules. When 5 molecules are aligned, when 5 dipoles are aligned, into 5. After some time, you increase the electric field strength. You increase the electric field strength. If you increase the electric field strength, here induced electric field strength is here, this, and this is the net electric field. After subtracting E naught minus EP, then E comes. You know E comes. That is yellow E naught, because E naught is more than EP. So E comes. So more will be the value of E. More will be the value of E naught. More will be the value of E. Accordingly, more and more dipoles gets aligned. 5, 10, 50, whatever the total dipole moment now, gradually increase. To which extent the dipole is now the dielectric gets polarized. To which extent the dielectric gets polarized, whether all dipoles are aligned or few dipoles are aligned. How will you know? I know that from dipole moment density, or that is called polarization. So polarization is called dipole moment density, already defined as the net dipole moment induced per unit volume. The net dipole moment induced per unit volume. Dipole moment induced per unit volume. So this is called polarization. Why we need polarization? To know to which extent this dipole is polarized. Means how many molecules gets aligned. Whether 5 or 10 or 50 or all. That one we will discuss. Okay. So what is the polarization? Polarization symbol will write P. Suppose n number of molecules are present per unit volume. I told you total dipole moment per unit volume. If n number of molecules are per unit volume and dipole moment of each molecule is P, then polarization is n into P. Small p is the dipole moment of each molecule. Small n is the number of molecules per unit volume. Or I can say this one, right? I can also write this net dipole moment by volume. Whole volume of the dielectric. What is net dipole moment? See, this is sigma surface charge density. Suppose this charge is, I am writing minus QP, total charge minus QP. Here total charge plus QP. Then minus QP plus QP. Now two charges as if two charges separated by d distance. So can I write QP into d? Total dipole moment is QP into d. Can I write? Divide by what is the volume? A into d. So d cancel. What is QP by A? Sigma P. QP by A is sigma P. So what is polarization? Polarization is also numerically equal to induced surface charge density. Can come as a 2 marks question. Prove that polarization is equal to induced surface charge density. Okay. So this is about this polarization. Now we got also one information from here. And this polarization is unit, it's a dimensional formula, always comes in exam. Unit you can write, this is dipole moment by volume. Dipole moment is what? Q into 12 by volume. Okay, dipole moment coulomb. This is 12 meter by volume is meter cube. So coulomb per meter square. Just same as the unit of surface charge density. Always comes in exam. What is the unit of polarization? What is the dimensional formula of polarization? You can find the dimension I am finding here. You see, it's coulomb A1 D1, and this is L square. Then you do it. This dimensional formula and unit always comes in exam. As a unit, I told you only. Okay, so this is about the polarization. But this polarization P will be more if the electric field will be more. This electric field will be more. Then this is also more. This depends on what? Depends on this. Also depends on this. So this P directly proportional the electric field inside the dielectric. Remember, its direction is not to this one. Electric field inside the dielectric. Okay, and epsilon naught is multiplied to make a dimensionally consistent the same thing, and one constant will multiply here. What is the constant? Now this is direct proportional. When I remove the direct proportional, one constant I will multiply. So that is, now this is the constant psi. Okay, this is the constant psi and multiply. What is this? Electric susceptibility. This constant is called electric susceptibility psi. Now you understand what this psi, what the physical significance of psi? How easily a dielectric gets polarized. It is the physical significance. All dielectrics not easily polarized. Some polarize immediate, some takes longer maximum electric field to gets polarized to develop dipole moment. Okay, so this is a quantity, this is a constant called electric susceptibility. Physical significance is how easily a dielectric gets polarized. Now you understand? Okay, so every dielectric has one susceptibility value. How easily it gets polarized? Every dielectric has one susceptibility value. Susceptibility determines this. Every dielectric has one dielectric constant value. How much electric field will be inside it? That physical significance of dielectric constant is how much electric field can be inside it, can pass through it. And susceptibility means how easily it gets polarized. Is there any relation between dielectric constant and susceptibility? Yes, there is a relation. How will you find the relation? Dielectric constant and susceptibility means relation between K and susceptibility. Yes, there is a relation. Let's find the relation. E equal to E naught minus EP. This E is equal to E naught minus EP. And now this is 1. Take the E to this side. So E naught by E, this is EP by E. So this is 1, and what is this? I have told you dielectric constant, and EP is the electric field inside it. Okay, so electric field inside it, that is nothing but sigma P by epsilon naught. This EP. Okay, electric field. This is the sigma P is the charge density, surface charge density. Okay, sigma P by epsilon naught. So 1 K minus what is sigma P? This is P. What is sigma P? This is just before I told you. Polarization is equal to surface charge density just before I told you. Okay. So 1 is equal to K. What is P again? Chi epsilon naught E. So epsilon naught. So is equal to 1 K minus chi. So is equal to, now K equal to 1 plus chi. Some are telling this chi, some are telling this psi, doesn't matter. Okay, it's just a symbol. Okay, K is equal to 1 plus chi or 1 plus psi. So this is the relation between dielectric constant and susceptibility. Now let us understand what is dielectric. Many more things today we will discuss. What is dielectric? Why dielectric constant of metal is infinite? Why electric field inside the metal is 0? Why when we keep the dielectric electric field or electric force decreases? So many more doubts today get clear. Another one is left. What is dielectric strength? What is dielectric strength? Now we will go to that one. Suppose one dielectric is here. You see, this is the dielectric. Or I am telling about one molecule. You think only about one molecule. This is one molecule. It's a positive and negative center concept. Positive and a negative center concept. This one value. Okay, you know dielectric doesn't conduct. It cannot conduct electricity. It is perfect. It is not perfect. It is an insulator. So this is plus minus. But if I give external electric field, now what happens? This molecule now becomes like this. Its negative center comes to this side, positive center comes to this side. This is external electric field. Okay, negative center comes to this side, positive. Now dipole moment is induced. I told you increase the electric field. When you increase the electric field, the minus plus gradually get more and more separated, more and more separated. Now you think, become more and more separated, more and more separated, more and more separated, then what will happen? Get completely separated? Yes, this happens. This happens, this minus plus get completely separated. Now you see this is minus, this is plus. HCl molecule now converts into H plus and Cl minus ion. This happens. They converts into ions. So even if in air, suppose now this room, in which room you are sitting, what is here in this room? Air, oxygen, hydrogen, nitrogen, air molecules are there. Okay. So dry air, I told you, it's a very excellent dielectric. Molecules are there. Some has dipole moment, some do not have dipole moment. It's okay, no problem. But now suppose both walls become immediately in this room. One wall become positive charge, one wall become negative charge. What happens to the air molecules now? They get polarized. Plus minus get separated. The molecule get polarized. Suppose now the switch is in my hand. I increase the electric field strength of this room. I increase the electric field. So one positive plate, this wall become more and more positive, and another wall become more and more negative. Now what happens to the molecules now separate, plus minus get completely separate. The whole air in this room converts into ion. When converts into ion, it can conduct electricity or not? Yes. Now start conducting electricity. From this positive to negative, now the charges, the positive charges moves towards negative plate and negative charges moves towards positive plate. Immediately electric current pass in this room. You are now asking the question, sir, in air current pass? Yes, in air current pass. Have you seen this? Have you realized this? No? In practical life? Have you seen current in air? Have you realized this? You have not realized anywhere. Whenever you learn physics, always go to the practical situation, practical life. If you are not realizing in practical life, then don't read that. Because nothing is there in physics which doesn't happen in the practical life. Have you seen where air becomes also conductor and current pass? Yes, in lightning. What happens in lightning? Air becomes conductor. I will tell you that one. But before that I am telling you how the air is an insulator. But current pass in air, yes, this happens. How this happens? When you increase the electric field strength, how much it will tolerate? How much it will tolerate? You are now giving excess electric field. It cannot tolerate, it cannot withstand. Then it breaks its dielectric nature and converts into, breaks its insulating nature and converts into a conductor. So what do you mean by dielectric strength? Dielectric strength is the external electric field which a dielectric can withstand without breaking its insulating property. When it breaks its insulating property, the maximum electric field which it can withstand without breaking. That is the dielectric strength of a dielectric. Maximum electric field what it can withstand without breaking its insulating property. So that is called dielectric strength. What is the dielectric strength of air? You know, dielectric strength of your air is 3 into 10 to the power 6 volt per meter. This is the dielectric strength of air. Means in 1 meter distance, this is electric field. Volt per meter means dielectric strength is the electric field. Okay, volt per meter means in 1 meter gap. Don't make the electric field don't make the potential difference 3 divided by 6 means 3 megavolt in 1 meter gap. If you make a 3 megavolt in 1 meter gap and you are sitting inside it, immediately current will pass. This happens in lightning. Okay, so this is the dielectric strength of air. Air will withstand this much electric field maximum. You remember, if you give more than this, then that air converts into a conductor. The dielectric breaks insulating nature. But what is the dielectric strength of vacuum? Do you know? Vacuum is the excellent dielectric. Do you know what is the dielectric strength of vacuum? 10 to the power 12 megavolt per meter. It is more, 10 per 8. That means 10 per 8 volt per 18. 12 plus mega means 6, 18 volt per meter. This is the vacuum dielectric strength. Much more, because there is nothing in vacuum to polarize. Much more. Okay, 10 per 18 volt per meter. But I told you to tell what happens in this lightning. You know, in lightning what happens? You know the cloud, how lightning happens. How lightning happens? You have, I think, little knowledge about it. In cloud, you know, the cloud molecules, the water particles, they get friction with each other. That is everything is physics, electricity here. Due to friction, charges develop. Also friction with the air. When cloud travel, also friction with the air happens. Friction between them happens. The positive part become, this upper part become positive charge, lower part become negative charge, and this is your mother earth. Okay, so this is your mother earth. What happened? So when this part become negative charge, immediately earth become positive charge. Why? How earth become positive charge? By induction. By induction, earth become positive charge. When earth become positive charge, you see there is a potential difference, and potential difference becomes much more high. So high that the air between it now converts into conductor. Dielectric breakdown happens. It increases it becomes more than dielectric strength of air. So immediately current comes. Your electrons pass now to earth. Electrons will come to earth now, current pass. And when current pass, you have seen when you see the lightning, what is the figure of the lightning you have seen? Lightning figure you see like this. Why the lightning figure is like this? Why not only straight line? Why it is like this zigzag path? Just like you have been telling that our god Indra, it's the weapon of Indra's Vajra it's called. Okay, why this happens? Why it is like this, having so many branches of the weapon? Because there is no specific path. When there is no specific path for current, it can go in any direction. Where it has little potential difference less, it go. As you have given no specific path, it will go like this, randomly, like this, randomly go. You just think, if you just, suppose you pour some water. If you pour water in a pipe, water passes through the pipe. But if you just pour water on the floor, where the water will go? Where the water will go if you just pour the water on the floor? Everywhere, little amount of this, little slope towards this point, making the branches it will go. The same situation happens what weapon Indra use, the lightning, Vajra. Okay, because no specific path is there. The air converts into a conductor. Dielectric strength breakdown happens. This is called dielectric strength. Now you understand what is dielectric strength, everything. Thank you. With this, our second chapter is now completely over. And one question from this polarization came in one CBSE sample paper in 2-3 years back. In CBSE sample paper, that question may come in your exam, but I will discuss that question in your next question answer videos. I will discuss the question. You just follow me. Thank you.